Okay, so in today's lesson, we are going to be talking about how we can use the skill of stoichiometry along with the ideal gas law. So that's what we're going to be focusing on. And again, you should probably want to have a periodic table out, maybe your calculator, in addition to your note packet. Like I was saying, we are going to work on using stoichiometry to identify, or I guess solve, conversion problems with gas laws. Now, in this thing, or in this first slide here, we need to talk a little bit about something called standard temperature and pressure. So standard temperature and pressure are basically reference points that scientists have agreed upon that allow us to try to make similar measurements all the time. The issue is that standard temperature and pressure occurs at at sea level. I'll deal with that. I don't know why that happened. Okay, so it occurs at sea level. And what that really means is that sea level, by definition, is a low point where the land essentially comes into contact with an ocean. And since we don't live near an ocean, we are definitely not at sea level. We are actually really quite far above sea level. But these conditions are what many scientists will agree upon in terms of comparing what you observe from data you collect to what we think to what we can calculate will actually happen. So the value of standard temperature and pressure conditions are 1 atmosphere would be the pressure, and 273 Kelvin would be the temperature. So in a problem, like for homework or something, it might say something like, calculate the volume for this gas at STP. Or it might say, calculate the number of moles of particles of this gas at standard conditions. And when a problem or a quiz or something like that says that, we're talking about the pressure will be 1 atmosphere and the temperature will be 273 Kelvin. And that's just something you kind of need to know. So we will probably give you those. We'll give you those on a quiz, but you just need to know what that means and how to use them. So now we're going to talk a little bit about stoichiometry and the ideal gas law. And in the past, this semester, right before spring break, we learned about stoichiometry by talking about converting from mass to moles to mass. That hopefully should look familiar to you, right? When we calculated mass to moles to moles to mass, when we go mass to moles, we need to use the molar mass, which is a value that you can grab and or calculate off of the periodic table. When you go mole to mole, we needed to use the mole ratio, right? And the mole ratio was comes from the balanced chemical equation. And then we go moles to mass, we still need to use the molar mass, which again is something that we can calculate off of the periodic table. However, when conditions are considered to be standard temperature and pressure conditions, there's a new relationship to this flow chart that we can use. And that new relationship or measurement or value that we can work with is volume. So we can go from like mass to moles, moles to moles, moles to volume of a gas. Okay. And when we do that, the relationship that we need to keep in mind is that 1 mole of any gas is equal to 22.4 liters of that gas again, at STP. So now we can go through the process of doing some type of stoichiometric analysis and consider volume of a gas as part of that process. So remember, at STP, 1 mole of any gas is equal to 22.4 liters of that gas. And that's at STP. So how does this work? Well, we're going to do an example here. And so one of the things I'd like to point out, first of all, is that this problem says that it's at STP. But even though this problem is at STP, that tells me that we could, that we can use stoichiometry as a shortcut. As a shortcut when dealing with volume. And so just like before, I usually go through the process of identifying my variables. So I'm going to have a pressure. I'm going to have a volume. I'm going to have the number of moles. I'm going to have the ideal gas law constant. I'm going to have temperature. But what's going to be different this time is we're now going to add mass, which will be grams. So just because I would like to reiterate what standard temperature and pressure is over and over and over again, because I want you to be comfortable with using it, is that when the question says how many liters, so we're solving for volume of H2 gas. So we're looking for this as our answer, will be produced at STP, right? So at STP, we have to remember that that's 1 ATM, and that's 273 Kelvin. And so we now have enough information. Oh, we have one more thing we have to deal with. Sorry. So now we're also told when 4.6 grams of sodium react. So we have 4.60 grams of sodium reacting in this reaction. Now, what's important here is that we have to identify is that this problem is asking us to compare sodium with hydrogen. So it's asking us to compare sodium with hydrogen. And because we're going to use stoichiometry as a shortcut, that's going to become important in a minute. So this problem is going to be a mass to mole to volume problem. Now, just like we talked about, when we go mass to mole, we're going to use the molar mass. And we go mole to mole, we're going to need to use the mole ratio. And so that's nothing that's what we've been doing, so that's nothing new. But when we go mole to volume, because we're at STP, we're going to use 1 mole of gas is equal to 22.4 liters of gas. In this case, the gas in question is H2. So because it's a stoichiometry problem, I'm going to take the 4.6 grams of sodium and put it over 1, just like we've done in the past, and go mass to mole, mole to mole, mole to volume. When we go mass to mole, we need to use the molar mass, which is the value of whatever it is on the periodic table, or the sum of those things. In this case, sodium is the molar mass we have to calculate. So I have 1 sodium times 22.99 grams will essentially give me 22.99 grams of sodium in 1 mole. So I want to cancel out grams of sodium in my problem. So I'm going to put 22.99 grams of sodium on the bottom and 1 mole of sodium on the top. In the case of the next step, when we go mole to mole, we're going to need to use the mole ratio. And when we use the mole ratio, I can see that the mole ratio between sodium and hydrogen is for every 2 moles of sodium, there are 3 mole, not 3, there's 1 mole. I should make that green. Shoot. There's 1 mole of hydrogen. So I'm going to set this problem up so that I can cancel out moles of sodium. So I'm going to put 2 moles of sodium on the bottom and 1 mole of sodium on the top. Nope, not sodium, H2 on the top. And at this point, I've gone mass to mole, mole to mole, and now I'm going to go mole to volume. And when I go mole to volume, I need to use this relationship here. So I'm going to put 1 mole of gas, which in this case is H2, on the bottom, and 22.4 liters of H2 on the top. I'm going to grab my calculator, and I'm going to calculate straight through. So I have 4.6 going across the top times 22.4. I'm going to divide that by 22.99 and eventually by 2, and I get a value somewhere around 2.240974337. So we now need to assess significant figures. Okay. So in pressure, that measurement there is 3 sig figs. The ideal gas law constant is infinite sig figs, and the temperature is 3 sig figs, and the mass in the problem is 3 sig figs. So my final answer's got to have 3 sig figs. So 1, 2, 3. That 0 does not round that 4 up. So again, my final answer is going to be 2.24 liters of H2. Questions? Yes, sir.
So wait, how did you get 22.99 grams of... Wait, no, I was looking at the wrong one. Sorry.
Okay.
I did that one.
Good catch. All right, so let's take a look at the next problem, the next example problem here. In the next example problem, I know that I'm going to be dealing potentially with a pressure, potentially with a volume, maybe with a number of moles. The ideal gas law constant is always my friend. Temperature, and now that we've learned about it, maybe mass. So when I read through this problem, the problem says how many grams of KClO3 are needed. So I'm going to be solving for grams of KClO3 are needed to produce 5.00 liters of O2 at STP. Well, STP tells us that that's 1 atmosphere, and my temperature is 273 Kelvin. And because this problem is at STP, we can use stoichiometry as a shortcut. So this problem is asking me to compare oxygen and potassium chlorate, KClO3. So it's asking me to compare those two things. And because the given value in my problem is the 5 liters, that's what I'm going to start with. So I'm going to put 5 liters of O2 on top and put it over 1. So this time I'm going to be going from volume to mole to mole to mass. And just like before, when we were going volume to mole, we need to use the relationship that 1 mole of gas is equal to 22.4 liters of gas. When we go mole to mole, we need to use the mole ratio. And when we go mole to mass, we're going to use the molar mass. So this problem, I can tell by looking at it, is going to be that number of steps. So what I need you to do now is I've kind of given you the problem. I've given you some of the starting materials here. I want you to take the time and solve this problem right now, and then we'll check through. Ready, set, go. Okay, so you've had an opportunity to try it, and maybe you worked your way all the way through. Maybe you need a little bit more time, but I kind of want to touch base here. So many of you remembered or recalled that you needed to use the relationship that 1 mole of gas is equal to 22.4 liters of gas, and you needed to set it up so liters cancels out. So I had 1 mole of O2 over 22.4 liters. We then went to the mole ratio, and because we were comparing KClO3 and O2, it was a 2 to 3 ratio. And then you calculated the molar mass of KClO3 to be 122.55. And then when you threw that in your calculator, you should have gotten something like 18.2 grams of KClO3. Questions? Okay. Now, this is great because it's at STP. We can use what I call the stoichiometry shortcut. But most of us don't live at sea level. And as a result of most of us not living at sea level, we have to be able to do calculations when we're not at sea level, which is what we're going to do now. So, because not everything occurs at sea level, we're doing a similar thing, but it's going to be a 2-part strategy or 2-part problem. Basically, we'll be using stoichiometry to either figure out moles or mass, and then we'll be using the ideal gas law to finish up the problem or even to start the problem. So one of the things that we can kind of point out here is that if grams are given in the problem, we'll use stoichiometry first. And if grams are not given in the problem, we will use the ideal gas law first. So it's just something to consider. Now, as we go down to do a problem, let's kind of start by identifying our variables. So P, V, N, R, T. And then mass is always a possibility now. So the problem says how many grams of NaN3 are needed to decompose in order to form 36 liters of gas. So we're going to be solving for grams in this problem. and we're going to be comparing grams. And according to what I've been given, or what I can identify, is we're forming 36 liters of N2. So I have 36 liters of N2. The gas happens to be measured at a pressure of 1.15 atm. And the temperature that the gas is collected at is 299 Kelvin. So in this problem, because we are solving for grams, we don't have grams in our problem, we are going to use the ideal gas law first. So step 1 says use the ideal gas law to solve for, in this problem, it's going to be moles of N2. And so when we're using the ideal gas law, we're going to simply plug what we have into the ideal gas law formula, which again is PV equals NR T. So I'm just going to plug in my values that I have. So in this case, I have 1.15 atm. Thank you. You're good. And I have 36 liters. And we're told we're going to be solving for moles. So that's going to be N. We know that the ideal gas law constant is going to be always 0.0821. And that'll be atm liters per mole per Kelvin. And then we are at a temperature of 299 Kelvin. And just like we did yesterday, we are going to simplify what we can. So I'm going to take the 1.15 times 36, and that gives me on the left side, that gives me 41.4. And my unit would be atm liters. And we're still looking for N. And we're going to simplify on the right side the 0.0821 and the 299 Kelvin. And we get something like 24 0.5479. In this problem, the Kelvin is canceled out. So our unit here is going to be atm liters moles per moles. And because we're still solving for N, we're going to divide the 41.4 by the 24.59. So 41.4 divided by 24.59 will give me a value somewhere around 1.68 649 8641, and that's going to be moles of N2. So that's step 1. Step 2 is to use stoichiometry to convert moles of N2 to moles of Na3N to mass of Na3N. So, just like we've done before, I'm going to now take my new value for moles of N2 and take that 1.686 moles of N2 and put it over 1. I'm now going to go mole to mole, and then I'm going to go mole to mass. Pardon?
You don't round it yet?
You can, but I usually keep it in my calculator. It would be 3 sig figs if you wanted to round it, I guess. So now we need to identify our mole ratio, right? So in this problem here, like I've already said that we're comparing nitrogen to sodium nitride, Na3N. So my mole ratio is going to be 1 mole of N2 for 2 moles of Na3N. And I'm going to set this problem up so that moles of N2 cancel out. So I'm going to put the 1 mole of N2 on the bottom and the 2 moles of Na3N on the top. So we used our mole ratio. And now, because we're going to grams, we need to use the molar mass. And we're going to use the molar mass of Na3N. So over here I have 3 sodiums times 22.99. And I've got 1 nitrogen times 14.01. So 68.97 plus 14.01 is 82.98 grams in 1 mole. In this case, it's going to be of Na3N. So I want to cancel moles out, so I'm going to put 1 mole of Na3N on the bottom, and I'm going to put the 82.98 grams of Na3 on the top. So again, at this point, I'm going to take the 1.686 something 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 times 2 times 82.98. And my calculator gives me an answer of like 279.8913 dot 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 dot. And now we need to assess significant figures. So the pressure that's given in the problem is 3 sig figs. The volume in the problem is 2 sig figs. The ideal gas law constant is infinite sig figs. The temperature is 3 sig figs. So my answer needs to have 2 sig figs. So I count 1, 2. That 9 does round that 7 up. So my final answer here is going to be 280 with no decimal point grams of Na3N. So hopefully it doesn't seem too incredibly awful. It's a 2-step scenario. But we're going to keep trying another one, which hopefully, again, won't be too bad. But it's going to kind of be the opposite of what we're doing, what we just did. So here we go. In this second problem, I'm going to identify my variables once again. So P, V, N, R, T, and then we're also going to be including mass now in grams. So the problem says, what is the volume of F2 gas? So we're going to be solving for volume. That's measured at 1.10 atm. and has a temperature of 308 K, and that's needed to produce the 10.6 grams of NaF. So this problem is comparing NaF and F2. Okay. So in this problem, because we're given a mass, we're going to do stoichiometry first. So we are going to use stoichiometry to convert mass of NaF to moles of NaF to moles of F2. So in this problem, I'm going to take the 10.6 grams of NaF, and I'm going to go mass to mole to mole. Would like you to take a moment and do this one on your own. Okay, so for this part of the problem, you had to go from mass of NaF to moles of NaF to moles of F2. So you needed to calculate the molar mass of NaF, and walking around, many of you calculated the molar mass of NaF. But remember, it has to cancel out the 10.6 grams, so that's why I have it on the bottom. We then go to we go from moles of NaF to moles of F2, which we use our mole ratio for. And our mole ratio in this case, we're comparing fluorine F2 to NaF, sodium fluoride, and it's a 1:2 ratio. And I set it up to get the moles of F2, 1 mole of F2 on top, multiplied across the top, and then divided, and I ended up with 0.126. Okay. So then the second step here in this problem is to use the ideal gas law to solve for volume of F2. So our ideal gas law, as you recall, hopefully, is PV equals NRT. And I know that the pressure, because it's what I've been given, right, is 1.10 atm. I'm solving for volume. The number of moles I just calculated was 0.12622 moles. Actually, I should do this. I have the R, which is 0.0821 ATM, liters per moles per Kelvin. And we know the temperature for this problem is 308 Kelvin. So I'm going to combine what I can, which means I'm basically going to combine everything on the right-hand side. So my 0.126 times the 0.0821 times the 308. So to rewrite what I have here is I've got the 1.10 ATM times volume equals, it's like 3.191713 and so moles have canceled out and Kelvin has canceled out. So the unit that I have over here is going to be the ATM and the Kelvin, and the liters volume. Now I'm going to divide both sides by the 1.10, so I'm going to divide that by 1.1. And my calculator is going to give me an answer for a volume to be something like 2.9015571514. Now, significant figures. The pressure is 3 sig figs. The ideal gas law constant is like infinite sig figs. The temperature is 3 sig figs. And the mass that we started with was 3 sig figs. So my answer has to have 3 sig figs. So I'm going to count, and I'm going to see that 1 cannot round that 0 up. So my volume is going to be 2.90 liters of F2. So those are the 2-step problems that you're going to come into contact with as we practice these things. The key here is to identify what you've been given. If you've been given a mass, you do the stoichiometry first. If you're asked to find a mass, you do the stoichiometry second. Okay. We'll have plenty of practice on this tomorrow in class. So enjoy.